Okay, very important. Remember to balance your first equations. If your first equation is not balanced, you keep going, right? It will be very disastrous. Okay, stop here first. Okay. Is it all kind of neutralization you will always form salt and water? Yes or no?
Should be lah. That's a theory.
Should not be. That's what we learned in Exam 4. Okay. Welcome to the A level. No longer there. Okay. Don't always force yourself say acid alkaline must give you salt and water. No. Okay. Now it's all about proton toner and proton acceptor, those things, Lewis axis and whatever. So remember, especially in this case, okay. Strong acid, strong base, no issue. Same thing. Strong acid. Weak acid, strong base, also no issue. The equation will look the same. But only weak base with strong acid, right? It will be different. Okay?
Weak base is strong acid.
Yeah, but just take a look. Okay? Just take a look. Okay? Now, the neutralization of NH3 with HCl, right? Okay? Will just become like that. No more. Okay? There's no water there. Okay, so now you must check, okay, do I have water? You may not have. Okay, so just like that.
So the second step, where you get the water from?
The water is always in the whole solutions.
Oh, from the...
Okay. But what I mean is that the water is not...
the
water actually is involved in here. But you have both sides. Because you know aqueous ammonia is supposed to have this. Okay, so, but you just get cancelled off. So we'll just out for equation, okay? Okay, your notes may be very well elaborated to show you some water here and there so that it will look the same, they can play around with. But in reality, we don't write all this already. We just straight away write this.
Oh, for the question, they will give us a number of moles of the concentration of
Yeah.
Of the NH3.
Yeah, at least how many times you have how many, right?
Yeah.
Yeah. So let's say 2 mole. Okay, 2 mole.
This is all in concentrations, right?
2 mole per, let's say 1 dm cube. Okay, let's double solution really is 1 dm cube. Yeah, we really pour 2 mole and 2 mole inside.
2 mole per dm cube.
Yeah, 2 mole per dm cube. 2 mole per dm cube, you pour 0.5 dm cube each so that you still remain as 1 dm cube. Okay, so that you can just work with 2 more easier. Okay? Okay, I want you to go through this process first, okay? All the variable number, they of course going to give it to you. Okay, see whether you can figure out how to find the pH of the result or not. Okay, now, step 1, you do this. Okay, so tell yourself, after reactions, how many this is there, how many this is there, and what's the second reaction? The second reaction is because it's ion, right? But nothing to do with this, right? So you only take out the ion, okay, come out something. So what is the next unit, right?
Plus water.
Plus water. What do you get?
NH3.
NH3.
OH minus.
Yeah. OH minus. So if that's the case, what equation are you going to write?
Okay.
Wait, NH3 OH minus, does it?
This is H3O plus. Okay.
Yeah. H2O plus, right? Yeah.
Also it's H plus.
H plus, yeah. H plus, then you don't add water, okay? So what is this? K what?
Ka.
Ka, good. Okay. Ka means this, and this.
This is a Ka of ammonium, right?
You're right. They got to give you the Kb, okay, at least. So you Kw over it to get Ka. Okay. So what's next? If they give you the Ka,
And then you x squared on top.
x squared, you're right. And below will be
2 minus
2 minus x, if this is 2. Okay. then rearrange, you put minus
then solve for
minus log
x.
x, then you get okay. Got it? Sure? Good. Hey, so let's come to buffer. Okay, what is buffer? What's the use of buffer?
Resist change in pH.
Yeah, okay, resist change in pH. So how does it really work? Okay. Now, so two things you need to know. First, you need to be able to explain. Okay, how does it work? Okay. Second one, you need to calculate. Okay. So explain, calculate first. Explain, you don't have to calculate. Calculate, you don't have to explain. Okay. So let's talk about explain. Okay. So just bluff. Okay. So buffer must form from buffer for two types. One is acidic buffer.
Yeah.
Okay, one is basic buffer. Okay, so what must it be there to form an acidic buffer?
Weak acid, strong conjugate base. Is it?
Weak acid and
It's conjugate base.
no, that's very bad. You don't need base.
Ion.
You're right. You need the ion. Okay, so
This is
if
the conjugate base.
this is conjugate base. You're right. You're right. You're right.
Base is
It's actually the salt. Okay, the salt of weak acid. That's what we normally say. You're right. And the conjugate base is this. Okay, acid and the conjugate base. Okay, so basic buffer will be the weak alkali. Okay, and the salt of weak alkali. Okay, for example, let's look at that. So how do you make a buffer? You can either pour one solution and solution of salt inside. Okay, or you can pour acid. Okay, and pour some alkali inside. So the sum of this acid then tries to form the salt. You will have this ion. Okay, so more than one way. Okay, don't always say there must be acid and alkali. Okay, so the idea is that how does this buffer work? Okay, it works actually due to the equilibrium of the system. Okay, the whole system will evolve in equilibrium. Let's take this one first. Okay, so H3COOH and go to CH3 COO minus plus H plus. Now that's an equilibrium system, right? And the property, according to the property of the weak acid or weak base, this guy like to stay at here or here, left or right?
left.
Left, right? It's not. When they love to stay at left time, there's no issue for them to shift to right because you have plenty thing at the left. Okay? But the point is that they will have an issue of further shifting back to left. Make sense? Because the right hand side got not enough. Okay? So what happens is that when you add a reinforcement of this ion here, okay, when you add a lot of the reinforcement ion here, you make this side to further push back here. Okay? Of course, this will be lesser. Okay? But then you have a lot of this and have a lot of this now. Okay? And this one, you only have a little bit. Okay? So the idea is that when you add a little bit more, okay, when you add a little bit more of this, it's easy to shift to the right because this is strong. I have a lot of this guy here, you add some more, that's enough for it to shift to the left. Okay? If you take away some, I have enough to shift to the right also. Okay? So the idea is because you have this kind of two step. Okay, the two step. It's just like a tube and a tube and a tube and channel the water level in this way. Okay, you have a lot of this guy. Have a lot of this guy. Okay, so like that. Okay, flow. Okay, if this one you change to lower, and there is a lot of this to push down and you raise it up. When you change to higher, there's a lot of this to help you to push down and make this back to this level, that kind of things. Okay? So I'm just trying to say is that you need both sides to have many ions so that you can always shift until this impact on the whole system is negligible. That means the equilibrium position will be very dependent on these two ions, but not so much about this ion.
But the mole ratio is 1 to 1.
Yeah, the mole ratio is 1 to 1. No, it's not 1 to 1. If you add extra inside here, right?
Yeah.
Then this to this will not be 1 to 1. And this to this will also will not be 1 to 1. Okay, you will have this one, you're going to be a lot more than this actually. Okay, because so anyway, when these two are in high concentrations, it's easy for the system to shift left or shift right to the equilibrium position, which is not so dependent on H plus. So when you disturb the H plus, you try to adjust it back to the same amount of H
I
plus.
thought the CH3COO minus reacts with the H plus to form the left side.
CH3CO minus, we have the H plus not formed as a, yeah, you're right. But then this equilibrium, right? Okay, equilibrium, right? So there will be a way that this amount push this amount. They cannot go all the way there, they cannot go all the way there, right? But
So if you add in a lot of CH3COO minus, the right side will be unbalanced.
the right side is
H plus will
unbalanced.
be fully
These two will
reacted.
certainly be unbalanced.
Means H plus is fully reacted and gone.
You'll be keep at a minimal amount. Okay, it's not gone, you still have some. But you can say it's nearly gone, you can visualize it. Okay? So this is why, right, this one is very negligible in the equilibrium positions. Okay? So therefore, if you have extra disturbance of H plus comes in, these two will be able to adjust it back. Now you want to think in this way, right? You must compare to what if I don't have reinforcement. Okay? If you don't have reinforcement, do you have any issue if you add OH minus? No issue. Why? Because when we keep neutralizing this with the OH minus at the time, this will shift to the right, will replenish the H plus. My solution will still be acidic, right? So long as it's not reached the end point of neutralization yet. Okay?
Is this reaction backward favored?
Now the original one without the reinforcement, right? Remember, majority of them love to stay in the molecular state. So very small amount will be in unlit state. H plus and whatever minus. Okay? So therefore, if you add OH minus at the time, that's what we always neutralize the acid with alkali. Remove this, right? When you add a few drop, it won't turn to alkali. Yeah. Because I still have so much of this can replenish this. Okay?
It's like the LCP thing.
Yeah, you can say so. But actually, the equilibrium positions is not so fair in the center. It's very biased because a lot of them love to live in molecular state. Okay? So if you keep removing, you keep replenishing. What does that mean? That means where it can actually retaliate your actions of adding OH minus. Okay? So the nature of this solution actually already can retaliate the OH minus.
Then what if you add more H plus?
Yeah, that's the issue. When you add H plus, the system cannot retaliate the H plus that you add. Why? Because I don't have enough A minus to keep shifting to the left.
But you see there's a lot of A minus also.
In the nature, if there's no reinforcement, right?
Yeah.
There's no reinforcement of this ion. Okay. Then it depends on the natural ionization amount. The natural ionization amount of weak alkaline is very minimal. That's what we learn, right? Okay, so therefore A minus is not enough to remove the H plus back to left hand side. So whenever you add the H plus, you will have a significant increase in the whole solution's H plus that you cannot retaliate.
So the best way for a buffer to work is when A minus and the acid is at equal volume. So
You're right. Then those maximum buffer theory comes in and you understand everything makes sense, right? So the idea is that when this one is low at the time, okay, you add a bit, I can shift left. You remove a bit, I can shift right. So this is how they add the buffer, okay, in the way that it works. Okay, so the explanations, okay, don't have to come so deep, okay, but if you understand this, right, you think that things make sense. Okay, so explanations, you don't have to explain all this. What you need to explain is that when H plus is added, how will H plus be removed so that pH is more or less unchanged? When OH minus is added, how come the H plus being removed will be replenished so that it will still remain unchanged, that kind of things. So you got to explain how acidic buffer will remove H plus, will remove OH minus, how's a weak basic buffer will remove H plus and OH minus for explanation. Any problem with that, those things? No issue, okay. So, understanding, explanation is done, let's do calculations. In calculation, any new formula that you learn, minus log of something, 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 is it? Okay. If you don't understand and think that it's too monstrous, try to forget it. Okay. I don't recommend any student to remember that way. Okay. It's very painful if you got to remember such a complicated things. Actually, you don't have to. The reason is that in the whole acid and alkali, we only have one equation. The one equation is the Ka equal to blah blah time whatever and whatsoever. Okay? So let's talk about acidic buffer. Acidic buffer have two things. The first thing is that you have a acid.
Acidic buffer means it works in the acidic region.
No. Acidic buffer means the buffer formed due to a weak acid.
Oh.
Okay? Basic buffer means that the buffer is formed due to a weak base or alkali.
So the example that you showed us just now, the addition of H plus wouldn't change the thing, is what kind of buffer?
Acidic buffer. Yeah.
But it exists in the pH region of 5 to 7, that range, right?
You're right, but that number is not very accurate, right?
But it's in the acid region.
Yeah, okay, because it would be, you have acid at the salt of the acid only. So you have acid, salt in acid, of course you're in the acidic region. If alkaline and salt of alkaline, salt for no pH contribution, we alkaline for pH contribution, then of course in the alkaline region. Okay? So don't take it as any alien knowledge, okay? It's just some common sense, okay? So let's do I need to come to the explanation for the how they remove the H plus or H minus? You okay, but you okay or not?
Yeah.
Okay, sure. Then we come to calculations, okay? So, any kind of acidic buffer, we have two equations, okay? These equations, and let's say sodium, okay, favorite, and this equation, right? Okay? So, do you have any formula for this equation? No, right? So, we only have one formula for this equation. And what is the formula of this equation? There's only this one. That's what you learn. So only this. Like, so any calculation you need to do, come back to here. You'll always be able to find it. Okay? Now, the idea is that if there's two assumptions here. Okay? The first thing you know in this system, this is reinforced by this. Okay?
Why by reinforced?
Reinforced because this one is naturally ionized, right? This is extra guys come in, right? And this is not reversible. So once you pour it in, it's the right hand side. Okay? The sodium plus will not take part in any reaction, so only this guy will be jammed up with this. So because of this, right, this indicates to you that the H plus concentrations cannot equal to the A minus concentrations anymore. Make sense? Because if this without this, H plus and A minus is got to be 1 to 1. You have this, you've got to have this, right?
I mean, so what's the experiment setup for this? 1 NA and
1 NaN. Okay, there can be many ways. Okay. So long as you give me this and this is good enough. Okay.
This and this come from what?
Any style you want. Okay. For example, you pour one test tube of HA.
What's HA?
HA acid. Let's say CH3COO minus. Okay. A is any anion. Okay. So, and then you pour one tube of CH3COONA. For the inside solution, you have a buffer. Okay. Or you have one portion of CH3COH, and then you come with the half portion of sodium hydroxide. Okay. Pour them inside, you still have kind of buffer like that. Why? Because this will neutralize this to form the sodium A. Okay. And you still have half portion of HA not reacted. So the solution will still have the sodium A and HA. Okay. So however way you want to make it, they are all possible. Okay. You don't have to always use neutralization method. Anyway, so this one, first one, you got to realize that H plus is no longer equal to the concentration of A minus. Okay, because A minus is being reinforced by the salt. Okay, how the salt form is up to you. Pour the salt inside, the salt is formed. Add the solid salt inside, the salt is formed. Neutralize some of the acid, you form the salt is formed.
Why the second one is a single arrow? That one also is good.
All sodium are soluble, right?
Yeah.
So they dissolve and ionize, and it's not backward.
It can't go backward.
It can't go backward, right? Because it's not it's a salt. Right? Once they ionize, they won't combine back, and there's no molecule you can form.
Oh,
Okay? But this is a molecule, right? It's a Yang issue, then you have this kind of ionizations, but majority still stay here. Got it? Okay? So let's come back here. Says that this two concentrations is not the same. Okay, so this is why you cannot make something square. Cannot make something square. Okay? Second, so the idea is that these are not the same, so you cannot mix H plus square. Okay, so Ka equal to this equations. What are the two assumptions there? Is that you need to learn in this system, you are very right to do two assumptions. Okay, the first assumption is that the concentration of Ha during equilibrium, okay, during equilibrium should be the original amount subtracted away the ionized amount, right? Okay, but think about this: when you have ionized amount, the ionized amount already small, and then you further reinforce the A minus here. You try to push a lot of H plus back to the left hand side, further, right? So this is why it's very close, very close to the original amount. Make sense? But can it be more than original amount?
Cannot.
It cannot, because the H plus must all dissociate from here. Okay? So you can keep pushing right to left, but you still cannot push more than what you give. Okay? Now, for example, I have 100 particle here. Okay? By nature, let's say, when you haven't added reinforcement, okay, let's say after you pour the HA, the ionized become 80 particle here, then 20 particle here, 20 particle here. Make sense? Okay? So what if I add a lot of this A minus inside and make it like, wow, 2,000 particle of this? Then the equilibrium will try to shift back to the left. But the point is that you cannot shift more than 20 particles to the left because you only have 20 of this guy. Okay?
Yeah.
So the most you can go back is, let's say, 19 of them. Okay? Then you get back the 99 particle of this. Okay? So that's why you cannot exceed the original amount, but get very close to the original amount once you add the reinforcement inside. Got it?
Okay.
Good. So this is the first assumption. And the second assumption you can have, right, is that the A minus that you will need in the equation is roughly equal to the A minus
Of the salt.
from the sodium A. Okay?
So you just throw in sodium A inside.
And it is equal to the sodium A's concentrations. The reason, the reason for this to this is because of this. Okay? If ion dissociates 20, by adding 2000, I got 2020. Okay? If 19 shift back to there, so my number is still remain as 2001, which is very close to 2000. Okay? So majority of this ion, A minus ion, will be due to the contribution from the sodium salt. And secondly, right, whatever you form from the sodium salts, the ion is the original amount because 100% ionized or sodium salt, soluble and ionized. Got it? So that's why all the way use this as the A minus. Okay? So therefore, the A minus concentration is roughly equal to the salt's concentration. Okay? Got it? So when you have this, put it inside here, and when you have original amount, put inside here, throw over here, throw over here. Ka is given, you can find pH.
Can you explain how to find the HA concentration? The first one.
HA concentration is the original amount given by questions.
So can you explain why again?
Because if you originally say, let's say 100, you dissociate a little bit, let's say dissociate 20, you get 80. But when you have a lot of reinforcement here, you try to shift back, right? But you cannot shift more than 20. So you get very close to original value only.
Is there any A form or you add in a new substance?
You add in external salt. You scoop some extra salt inside the exit. Okay.
What's the original main equation for the whole thing?
Sorry? Original equation is this only.
So the whole equation is what react what?
There's no reaction at all. It's just buffer solutions occur there that have its original pH. Got it?
Also, the solution that can buffer stuff, and this solution have a pH.
Yes. And this solution have initial pH. Okay?
Actually, everything has into pH also.
Yeah. Makes sense. Okay? Haven't started any solution, reaction yet. It says that if we have a buffer solution, the buffer solution itself should have this pH.
So that's called the pH of buffer.
Yeah, pH of the buffer. Okay, so this is why when we arrange this, we arrange that, take the minus log of everything and split this minus log of the product and the quotients, right? Then you have the very complicated equation of minus log of Ka la, salt la, and the original acid and descendant. Okay, but to me, I still recommend try not to remember that equation because things can change in between. Okay, this one, okay? Sure. Okay. Now, if this is okay, let's come to talk about maximum buffer. Okay.
Is there even a titration?
There's no titrations. In most of the time, right now, that's how come we get confused. We learn about neutralizations. Okay, we learn about buffer. We should learn it separately first, and then we realize that during neutralization there will be one instant that it turns to buffer, if it is a weak acid or weak base. But buffer need not always occur in neutralizations. Okay, it can be you can as what I said, you can have buffer, right? You can have acid scooped with the salt. Okay, two separate portions mix them together with a buffer. You can do neutralization, which is acid and alkaline.
At some point you have a salt that
Yeah,
acts as
some point that you haven't fully neutralized it, some of the alkaline and some of the acid will give you some salt.
But you
Okay.
still have some
Yeah,
acid.
but you still have some acid in excess, so you have acid and salt. So at that instant, it's still buffer. So before you reach the neutralization point, in weak acid or weak alkaline neutralization, you will have an instant of buffer. Okay. So during the buffer solutions, there's one thing called maximum buffer theory. Okay? Maximum buffer theory, or the maximum buffer point. Okay, it says that when that's what. Remember, okay, I draw this and H plus and salt reinforcement, right? Okay, it is when this is 1 to 1. Okay, when the acid amount concentrations is roughly equal to the ions amount or the salt amount. Okay, this is a maximum buffer. What's the meaning of maximum buffer? It will give you the best retaliation of whatever acid or alkaline added in the solutions. That means if you add a little bit of acid or alkaline in that specific region, it will give you the minimal change in pH. Okay?
So it's 1 point in the solution.
You're right. It's 1 point. Okay, so this is when this happens. Okay? So tell me, if I have CH3 COOH and I have another portion, I titrate with NaOH. Okay? If I have 1 mole of this, okay, I have 4 mole of this, 4 mole of acid. I want to make a maximum buffer solution. How many mole of this should be added?
4.
4. Is it? Sure? You? Guess?
I don't know.
Try number. Now, you want maximum buffer, you need these two to be equal. Okay? If you add 4 mole, okay, 4 mole alkaline will neutralize 4 mole acid. So you have 4 mole of salt. Okay? And then you have 0 mole of acid.
Or 8.
If you add 8 mole,
Then
then you have 4 mole of salt and 4 mole of alkaline. 2 mole. Right? If you have 4 mole acid, you only pour 2 more alkaline inside. You have roughly 2 more of salt. Okay?
2 more of salt, 2 more of unreacted
And you
acid.
still you have 2 more of unreacted acid. At that instant, your acid and salt, the concentration is the same. And then, according to maximum buffer theory, you are having maximum buffer at the instant. So take a look at all your graph. The buffer point isn't always at the center of the neutralization point and the initial point. It's roughly at the center, right?
Can you repeat?
The neutralization graph, okay?
Oh, as in, you
Yeah.
you add CH3COH to NaOH.
No, you add NaOH into CHCOH. You have 1 point of CHCOH. You keep dripping your NaOH inside. Okay.
Then
So if I originally have 4 mole of acid in the point of the things, okay. So how much I got to drip down, okay, so that it will have a maximum buffer solution, okay, which is the acid equal to the ion. How much do I need to drip from the burette? When you have 4 mole, okay, of acid, if I pour 2 mole of sodium hydroxide inside, 2 mole will react with 2 mole of acid. I left 2 mole of acid unreacted. And then 2 mole of salt will form due to neutralization. And then this inside I have 2 mole of acid and 2 mole of salt. Okay, 2 mole of salt give me 2 mole of anion, right?
yeah.
So 2 mole, they'll be equal. But that's maximum buffer.
So your 2 mole of salt form
Mhm.
would
2 mole of salt form will I will have 2 mole of
will
salt.
dissociate into ion.
No, you say in the ion, you're right. Okay, 2 mole of ion. Okay, sodium ethanoate, right? So 2 mole of salt form is 2 mole of sodium ion and 2 mole of ethanoate ion. Okay, 2 mole ethanoate ion, but initially I have 4 mole of acid, 2 mole got reacted, so I still have 2 mole left. So I still have 2 mole of acid and 2 mole of ethanoate ions. So my acid and salt concentration is the same.
So at this instant, addition of what will not change the pH?
Addition of both H plus or OH minus will give you the minimal change in pH. Okay, that means you have the best general gradient. Then you add a bit right, it will not change much up down. Okay, you retaliate how much you add, but it will not say totally don't change. Are you thinking too difficult things?
I'm trying to visualize.
Okay, now, so this is why, right, in here, in the beginning of a neutralization graph, right, you start in the weak acid region, okay, and then you say roughly you go in this way, and then get very sharp and then very sharp horizontal, right? Nothing like that. Well, this is what we call neutralization point, okay. And then we say that this is buffer regions, and you realize the buffer regions, right? This is the maximum buffer.
Oh, it's always fun.
This is always nearly like half of it. This is x. This will be roughly half x. Reason is because of this. Okay, roughly half x. Okay, so how to calculate the pH when you have maximum buffer solutions is even easier.
Just take pK.
Yeah, why?
Because I'm following the very complicated formula.
Oh, okay. Now here, we only have one formula. Ka equal to H plus and A minus and HA, right?
Yeah.
Maximum buffer occur. These two is the same.
KHA.
You're right. Okay, these two is the same, right? exit and the ion
So
are
it
the
can
same.
cancel.
So cancel become one to one. Okay, so this one Ka at this instant maximum buffer is Ka equal to H plus concentrations. Okay, so
Ka
minus log Ka is actually the pH at the instant, just like that.
Ka is a value.
Yeah, okay, they got to give you the Ka, right? Or else they will give you pH, right? To find Ka. Okay. Now don't take simple things too complicated. Okay, if you think too complicatedly, that means, yeah, you might need some time to realize it's actually simple. Any problem? Anything you want to ask? Any point you don't understand? Let's clarify once and for all. Okay, you see these equations, right? pH buffer. Wow, this looks how come they write until so cheap? Okay, now I take log. I rearrange first. Okay, H plus is equal to Ka times Ha and divided by A minus. Okay, then I take a log. Take minus log at both sides. Okay, so this becomes pH minus log 10 of Ka, Ha, and A minus. Okay, then you use the logarithm log. This will become Ka. Okay, if you make a big bracket here, plus log Ha. Okay, minus log, but I think they didn't do. They just put it here. Okay, so therefore minus log Ka minus log Ha over A. They won't absorb the minus log inside. They can rearrange that to A minus over Ha. Okay, and then they put this as the source, and this is the exit. This is original now. Okay. So my recommendation is to not to remember this. Just go back to the original one equation in the whole chapter. There's only one equation, and this equation makes sense in any point. It's not just in the buffer point. Okay, it's not the maximum buffer point also. Any point it makes sense.
Can you just do the description of the whole titration reaction between using this equation?
Okay.
And then you describe what happens when the first addition and so on and so on.
Okay. Yeah. Sure. Why not? Okay. Believe that it's simple. Okay. Now, the graph is in this way. So, the interesting features that they want to explain is the initial point. Okay, it is before it goes to and these regions. Okay, this is called buffer regions. Okay, this is initial point, and then neutralization point, and right after neutralization point, it should come to the end point. Actually, neutralization to the end point is. I don't think they talk about this. They're not talking this. Okay. 1, 2, 3. Okay. How many equations do we have? 1. Whole chapter there's only one equation. The one equation is what? Ka equal to in this case it is CH3 COOH H plus and OH minus. So Ka of H plus OH minus CH3 COO minus, CH3 COO minus, and CH3 COOH. Okay? So at this point initially, this is the formula. How much, because without adding any sodium hydroxide, okay, this is the amount of sodium hydroxide added. Okay, this is the pH, things like that. Now without any sodium hydroxide added, it is the initial point. So you only purely have this one pore inside your solutions. Okay, so that by itself it naturally dissociates with this and this. Okay?
Why?
Because this is in the solution form.
Oh, okay.
This is haven't started titration, but it's already in solutions, right? And the burette haven't dripped anything yet. You're still in the, it's still there. Okay, so anyway. Okay. Okay, this CH3COOH solutions. Okay. Okay, then you drip the sodium hydroxide. Okay. So before any drip, itself will dissociate in the beginning, right? So whatever. So
Only the weak acids will and weak bases will dissociate.
you're right. And strong base, you will totally dissociate. Will not have any remaining molecular site. There's no equation for it. There's no Ka.
So for weak acids and weak base, there's a mixture of ions and molecules.
You're right. This is why you have a Ka and Kb. Okay. So once you see Ka and Kb, because it's weak
So
acid
right from the start, there's a mixture of ions and molecules.
and molecules. You're right. A mixture of this and a mixture of this. Okay. If some of this on there. Okay. And since, right, you didn't add anything, didn't disturb any system, so this is the, this H, at this instance, right, the H plus concentrations is equal to the CH3 COO minus concentration. Make sense? Now, according to these equations, and you pour only this into solutions. Okay, now this is a powder, okay, solid powder form. This is a pond of water. When you scoop the powder, weigh it, okay, how many mole it is, you pour it into the solution and stir, okay, then it will have dissolved, all will dissolve because they're all hydrogen bond, okay, very soluble one, dissolved. But for those dissolved, only a few ionized to become these two. So majority still remain as this one AQ, the molecular aqueous state. Okay?
Can you,
Yeah.
you see this question, if you want to do your way, then
Calculate pH of a solution mixture of this ethanol acid with 100 kg sodium ethanoate.
yeah, just K equals to,
Yeah. So what they do? So you use this, right?
then I sub the concentrations inside, then I get K value, then I don't want to find H plus.
Wait, something is wrong because you no longer be 0.1.
Yeah, it's 0.05.
0. No, the how can this be 0.
This is the salt, right?
The salt. Oh yeah.
The salt starts out with this one. So you must divide by 2.
Let me see. Okay. Calculate pH solution mixing this and that acid and so this already the salt. So when you mix inside, you are diluting them to
Half of
0.1. Sodium ethanol. Yep, this 0.1. You're right.
and
Then this one is 0.005. Yep, good. And
I
then
write
it is
K.
110. Yep, good. Okay. We arrange
Yeah.
them that you get the H
How
plus
do you
concentration.
arrange?
Times this divided by this you got H plus, right?
Yeah,
Put a minus long before you got pH, right?
there's a pH of the solution.
Yeah.
But I got,
You got. Okay. Press calculate correctly. Let me check. It should
oh,
be-
I think I never times power negative 5.
Okay, good.
Okay, then
So at the start it has molecules and ions.
Yeah, and in the start, you see these two contributions are the same. Because
so anything happen at the start?
nothing happened, right? Start only. Yeah,
So you add B of NaOH, then what?
yeah, when you add NaOH that time, okay, add NaOH, some of this will react with CH3, COOH, okay. Some of this, right, will react with the sodium hydroxide, okay. And this with this, right, will form the CH3COONA and H2O, okay. Neutralize, right? So, but you just neutralize a portion of this only, right? So therefore, you will have this salt form, and you still have a lot of acid not reacted.
Then how about your ions?
The ions in the solution is it? You will have
When they react,
sorry.
the ions, the first part when it's dissociated into molecules and ions, right?
Uh-huh.
So when you add NaOH, it will react with the molecules, right? How about the ions?
It will react with the ion first. Okay. COOH self-dissociate become H plus and CH3 COO minus, right? Okay. Then sodium, you pour sodium hydroxide inside. When dissolved in solutions, sodium will form sodium plus and OH minus ion, and then these two, okay, will neutralize to form water. Okay. And the sodium plus is a spectator ion still remain. And then this, and once you remove the H plus, right, according to the Chatelet principle, this will shift to the right to replenish some extra H plus. So those you neutralize, right, yeah, it disappeared. Okay?
Okay.
This is a single arrow. If you put OH minus and H plus, it will become H2O form. Okay? So H plus is gone. But then the Chatelet principle will shift this to the right, so that you still have H plus come out again.
But wouldn't the NaOH also react with the CH3COOH, which
It will not.
make it move?
It will not. OH minus is only interested to react with H plus to neutralize with water.
Okay.
Make sense?
So the molecule forms of CH3COOH is not reacted.
You're right. Actually, it says that you want to react this, right, you keep shifting to the right. It's the ion at the right hand side which will react with the OH minus. I think this guy will choose this instead of choosing this.
So water will be formed.
Yeah, water
And the
will form.
CH3COOH will slowly diminish.
Yes, and then you can see more and more of this come out also.
So what would that ion form CH3CO minus?
CH3CO minus, yeah, will still be there. Spectator ion. It will not do anything.
So this will go on until when?
Go on now. You see, in the beginnings, from self-dissociate, I have a lot of concentration of this. And I already have some dissociation of this, and I have some dissociation of this. So when you add the sodium hydroxide, and you remove this amount. You remove this amount to form water. So according to Chatelet principle, this amount of things will be lost to replenish this amount come out. But once you replenish this, right, this will have more. Make sense?
So it will form a pool of CH3CO minus plus Na plus and H2O.
Yes. Now, if you keep pouring, you keep removing this, and this will keep drop, and this one keep increase. This one will still remain as a little bit increasing.
So the buffer is when?
This is already the buffer. When you have the ion concentrations, when you have the acid concentration, you already have the buffer. Because you already form CH3CO minus concentration.
So you mean at the start before you add NaOH is already buffer?
Not it is. In order to reach a buffer, you need to have significant level of the salt ion. Maximum is at the set. Maximum is when these two concentrations are same. Okay, but you can still say there are still some buffer. Theoretically, yes, why not? Okay, but significant buffer, right? When you say buffer regions, right, that means it can retaliate your addition significantly. Okay, and as what I said in the beginning, the natural acid system, right, is good on retaliating you adding OH minus. Because by nature, this have a lot, this have a B, this have a B. This is good to shift to the right. So you remove this, or you keep replenish this. Okay, so it's already good to retaliate addition of OH minus. Okay, but this system is not good in retaliating addition of H plus. because you have not at the start, you not have this. So you can say that in this case it works as a retaliation against the OH minus you added, yes. But on the other hand, a buffer need to work in both ways. It cannot work well if the H plus is added. Okay, you have a weak exit, you pour HCl there, the pH will change a lot. You cannot retaliate. Okay, so buffer needs two way. Got it?
So at the max buffer zone, the CH3CO minus ions and the CH3COH is equal.
You're right. That's the best retaliation in both sides. Okay, and you know, for you to have that, you need a lot of concentration of the salt ion. You want it to be more or less the same. Okay, that's the idea. On the other hand, if you neutralize too much the time after the midpoint, right? If you come to points like this, right, you have too much of this compared to too much of this, right? Therefore, you can see, right, adding compare this point with this point. Now, in this graph is all about adding of OH minus. Okay, so you can see is that in this point, right, you add OH minus, the gradient, right, is a lot sharper than here you add OH minus. Right? Why? Because at this point, right, it is bad in retaliating OH minus anymore. Because the exit amount, right, compared to the ion amount, right, now is in this way. If you add OH minus, remove it, right, you have not enough to shift to right. Okay? So these regions, right, is lousier in retaliating OH minus addition. So you see there's a big change in pH. Compared to this one, you add the same amount of OH minus to the right, it will not have much change. Okay? But on the other hand, right, in this point, right, it is bad in retaliating H plus attack. Okay? But this point is good in retaliating H plus attack. Okay?
Means you add more acid.
As in you add a bit, right, which side will change more pH. Okay? Now this, so it says that, okay, now because you can see, right, now this is the maximum buffer, right? But this gradient is even more gentle than this. How can I say this is a better buffer than this? Make sense, right? But a more gentle gradient means that you add, it didn't change much. The delta Y is small, right? Okay? So this point is even more gentle than this. How come you say this is a better buffer than this? Because this is good in retaliating OH minus, but not good to retaliate H plus. Okay? This one is the balance of both. So this is the maximum buffer for this natural system. You got to attack both sides. Okay? And this instance, when you have the right side is high, left side is low, now it starts to be lousy in retaliating OH minus attack.
So why is this half the equivalence point?
Sorry?
Why is the max buffer zone half the equivalence?
This one, right? It's a maximum buffer zone.
Yeah.
Yeah.
Is there a qualitative way to?
Yes. When the exit and the ion are the same concentration. That's what I say. Maximum buffer. Okay.
Yeah, but why is it half?
Sorry?
Why is it half?
Like half.
Why is it half of the equivalence?
Oh.
At equivalence point, there's no more acid.
Yeah, you're right. So maximum buffer, okay, is when your exit and the ion concentration is the same, okay, or roughly the same, okay. So let's say if you start with 4 mole exit, okay. So if you half neutralize bond, you're gonna add 4 mole alkyl, okay. Half mole or half bond, you're gonna add 2 mole of alkali. Okay. Okay. So 4 mole, 2 mole react, you left 2 mole exit. Okay. And then you form 2 mole of salt. Right? So you have 2 mole of exit, 2 mole of ion. So that's the instance where you have maximum buffer. Completely neutralize 4 mole, 4 to 4. Okay, so half of the 4 will give you 4 to 2, and then 2 more salt will form. So salt and acid are both 2. So that will be maximum buffer. Okay?
So the alkali is half of the acid.
You're right, roughly there. Okay? It might not be exactly because you still don't consider about the hydrolysis amount, okay? But it's roughly that. Okay, any more issue about buffer? Okay.
Yeah, actually I'm doing this question. There is B2, I'm doing the your way, and then I got 4.93.
4.9 something. Is it correct?
Answer is 5.0, I think they got round or something. Can you tell me?
Okay, sure. Let's do. Okay. 5. The part B, is it?
Yeah, part B part 1.
B part 1. Can you do part A? Nothing to do part A, right? Okay, on the page, if this and that
Actually, not really much.
are added to one of the above buffer.
I think your way is quite complicated because I need to calculate the number of moles, then change to the number of the concentration.
Oh, you don't have to.
Oh,
You don't have to. You just change inside because the denominator is the same.
really?
Yeah.
Can you go through?
Oh, sure.
One question.
7B1 example. Have a new pH of 1 cm cube of 1 molarity of HCl. We add it in the buffer solutions. Oops. Your buffer solutions, then you have the same thing of 1 cm cube of sodium hydroxide. Same thing, sodium hydroxide. 1 dm cube of buffer solutions. Okay, so what's your buffer solutions? Your buffer solution is made up of this. So in the buffer solutions, CH3 COOH concentration 0.05 m, CH3 COONA, which is the same as the ion, okay, which is equal to 0.1 m. Therefore, in part A, you know that pH is equal to 5.1. Okay, good. Thanks. Now, so when you add 1 cm cube of this into 1 dm cube of this, okay, you added 1 cm cube of 1, so
0.001
0.001.
mole of H plus.
Ah, cool. Okay,
Yeah.
so what do you have? I have the equation wise, I only have Ka equal to H plus H plus and CH3CO minus, right? A minus and HA, right? So when you added this, do they do the exact things?
They do the formula.
They do the formula one. That means they didn't. Oh, they do the 50-50 things. So they also have to do the.
Yeah, it's only to find mole and change concentration.
So is it the same? I still have to do all this the same. To me, it's like I still do. I will still do 0.1 minus 0.001 over 1 plus 0.001, right? And then I still have to do a 0.05 plus 0.001 divided by 1 plus 0.001. Okay? Why I say I don't have to care, actually these two are always the same. And this only one variable, see? So you can always cancel it out, whether you want to calculate this or not.
Oh, so what's the show?
No, just later in the new concentration, right? New concentration is the new volumes. Okay, and then this is the number of mole, and this is the new number of mole, right? The assumption is that H plus comes in,
It will be absorbed by the CH3COO minus
and you expect that it will be absorbed by
to form CH3COOH.
and not double arrow here. That's the assumptions, right?
Yeah.
So if you add the 0.001 mole, this one 0.001 mole, you will need 0.001 mole of this to react with this. But this one lost 0.001 mole, so it lost here.
So the thing is, for this question, when if they add a H plus, it will be absorbed by the ion formed by the salt. If they add in OH minus, it will be absorbed by the
H plus
acid,
to form H2O.
by the acid.
Yeah, but acid also can. Yeah. Then the amount of acid will be dissolved, and these things you need to. This thing is actually found in your explanation part, right? In the explanation time, you will explain how exactly the H plus is being removed by buffer solutions, right? So you will say who is the one that will weigh H plus, and who is the one to weigh OH minus, and how the thing will shift if you give better H plus and these things. Okay, then you just do according to what you explain. Okay, then you get H plus, and this is the same amount. Okay, and remember this, okay? Most of the system, right? They will be very nice to give you 1 to 1. So the denominator actually you don't have to calculate. Okay, this get cancelled. Okay, so you just consider number of mole, right? Is removed by how much? Number of mole here. Okay, what's here? Number of mole this. Now because of this, right? You form an extra 0.001 mole out. So that's why you add a 0.001 mole here. Okay, so this one added by so much, this one subtracted by so much, the Ka won't change, dump it over, you get H plus.
You know, for this question, right?
Yeah.
It's weak acid and weak base, right?
Weak acid with base?
Yeah.
Which one?
This question 7.
No, there's weak acid only, there's no weak base, right? Now, buffer solutions, you don't need acid and base, you need acid and the salt of the acid. Okay, the sodium ethanoate, right, is already a salt. The ethanoate ion is a salt.
This is not titration.
Not titration, yeah. Buffer solution is not titration. Okay, buffer solution can be prepared by just pouring acid with salt. It's good enough. Buffer solution can also be formed by acid with alkaline that will still generate the salt. So remember, the first thing is that do not remember the alkaline, okay? Remember the salt. Any more things behind? Good. Your notes is very good. Any more question on this? Any questions you want me to try here?
Oh, question. I think question 9 quite standard question.
I believe in this chapter, it's very hard to set a non-standard question.
Question 11 very
Okay. Let's try. Interesting. Working range of color of 3 indicated as below, blue, and this and that, below. Each color will use the test pH equal solution X, whose pH is 4.6 between color and each of the 3 indicated. Show. No issue at first one. The first part A1, do you need anything? We just see the range you say.
Oh yeah, this one only.
Yeah. So only
This
the
one,
part C1, right? Okay. The one you highlight, okay? Which of the 3 indicators we use for tension between equals ammonia and a bromocresol green is made of a weak acid which can be represented by XZ. What expression of defining Ka? Now this is important to do the easy part here. Okay, so let's do this. Bromocresol greens use XZ. Okay, so write the equations. If you bother, okay, now if you gas C, right, then you add H2O, then write H3O plus and Z minus, okay, but I don't care because I don't get subtracted mark by that. Okay, so done. Okay, Ka. And so dissolution constant and okay. Use the Ka equal to H plus Z minus and HC. Use the working pH range of bromine to show that KH or XC is this. Cool. This one takes your thinking. Okay, so-called working range, right? 1.2 to 2.8. What do you think about? Okay, just to straight away tell you, okay, all these are weak. All these kind of indicators are weak acid and weak alkaline. The working range, because the gradient at that range is quite gentle. Actually, all of them are buffer solution. Yeah, not wrong. Okay, and they are all buffer solution. So the maximum buffer, right, is always occur at midpoint. Okay, it's all the midpoint pH. You're right. So this is why, right, it says that the pH range of your bromocresol these things, okay, the pH is range from 1.2 to 2.8. So the midpoint is actually 4.0, which is 1.2 plus 2.8. I don't say finish, divided by 2. Okay, so it's 2.0. 3, 4, 4. It's 2.0. Okay. So at this instance of the maximum buffer occurs, right, this yield this. Okay, therefore Ka equal to H plus this. Okay. So if pH equal to 2.0, right, H plus concentration should equal to 10 to the power minus 2. So therefore 10 to the power minus 2, Ka equal to 10 to the power minus 2. Is it correct? Both. No, wrong. So what is your pH of? .2 and 2.8. 2.0, right? 10 power minus 2 kg. Ka is 2.5 at 10 power minus 5. Okay, let me take a look. Indicator. Company color 2, working range of exit. Cool, okay. Okay, that means the range is not about the buffer solutions. Sorry. Not so easy. Okay, the idea is that this side is color 1, this side is color 2. Okay, they define the working range as the after the working range, right? It will be exactly one side, one color. Okay, you will see one color. And when can you see a one color is that when you have this ion is more than or equal to 10 times of another ion. Okay, when the ion concentrations of XZ is greater than or equal to 10 times of this ion, okay, you will see the dominant color of it. Okay, when on the other hand, when this ion is having 10 times of more than this ion, you see the dominant color of this.
So why not 10 times, why in the middle?
That will be in the range which it's very hard to judge which color it is, a transition in between.
Oh.
Okay, so they define within this 10 times 10 times range, right, is called the working range here. Okay, at your note 6.2.3. Okay, so that they have this concept. Okay, actually we have this 0 to 14 in room conditions case, and then you have the working range here is pk your things, okay, plus 1, and pk your things plus 1. Okay, so this is the working range, and your so-called of course the k of HL indicator is equal to the Ka. That means it's the Ka of the indicator. Okay, that means it's a Ka plus 1, Ka minus 1. Okay? So, therefore, compared to the your questions, right, is you have the, oh, I copied the wrong one, no wonder. See. Gomo crescent green is 3.8 to 5.4, I copied the wrong one. Okay, so this is 3.8 and this is 5.4. Okay, so minus 1 is 4.4. We're there. This 1 plus 1 is 4.8, you know. Okay, whatever it is, okay, I think I got the wrong number. Okay, let's go back to 3.8 plus 5.4 divided by 2. I want to get the midpoint, which is what I have.
9.2 divided by 2.
Yeah.
Get 4.
4.6. Okay. So if according to just now what I say, I should get the concentration of your is 10 to the power of minus 4.6. Okay. So 10 to the power of minus 4.6. Which is still not 3.8 plus 5.4. 9.2 divided by 2, 4.6. 10 to the power of minus, open bracket, minus 4.6. Yep, correct. I got it correct. So it's 2.5 times 10 to the power of minus 5. Okay. That means I didn't follow the notes. That means I'm going to teach you my thing. That's why I say, okay, they're actually all the same thing. Okay. Now let's talk about what your school says. Okay. Your school says this onward is color 2, this before is color 1. So that is a transition, right? Okay. A transition, as what I say, a transition is actually where you can't see a sharp change in color or it's a gentle gradient, slowly color change. And what is so-called slowly color change, right? Is actually the buffer region. Okay? So buffer region is like that, so therefore the maximum buffer occurs is always at the center. Okay? So just now the number is I copied the wrong one. This is 3.8 and 5.4. Okay? So this is the pH. So maximum buffer occurs at the center. So you have 4.6. Okay? And maximum buffer occur, right? Actually, you can have Ka equal to H plus.
But maximum buffer you just K equals to.
You're right. These two cancel, right? So Ka is equal to the H plus.
Yeah,
right? And you have pH equal to 4.6. Therefore, H plus concentrations equal to 10 to the power minus 4.6.
Yeah.
Therefore, you can say that at this instance,
equals to
10 to the power minus 4.6. You press the calculator, it's equal to 2.5 times 10 to the power of minus 21 to the power of 8. Is your answer.
But how do I show it from the?
You just say back. I use the word maximum buffer occur when pH equal to 4.6. And how I get a 4.6? Okay, maximum buffer occur when pH equal to 3.8 plus 5.4 divided by 2, which is equal to 4.6. Okay? Let's start from this sentence, you can write all these things.
I got some questions. I really don't really understand. Like for when they add H, right? Because here is like that, I got this weak acid that is also said to this one, but most still stay as this one. And then this one is one single and this acid that totally ionized to form this one. And then when you add like OH inside, it will be absorbed by this one.
Yep. And then
it will be absorbed by this one, so right. It will change back to.
No, it will replenish. According to Sheldon principle, this will shift to the right to replenish the H plus that you removed.
So this H plus this new OH added will change into H2O.
Yes.
And then because this H2, because there is
H plus gone, we replenish the H plus until the same value.
Replenish the H plus so that
this one will drop by the same amount that you add in.
This acid will drop in amount.
Yeah.
And then because when you replenish H plus, you also so-called accidentally added in additional CH3COO minus.
If we add an H plus inside, the CH3COO minus will react with the H plus to form better molecular state of CH3COOH. This is why I say, do I need to go through the explanation part? This is very important things. That's how exactly you do all these questions, because you need to know how to explain. Okay. It's not good to say that the OH minus react with this. It's better to say OH minus removed by H plus. Okay, and then the Sheldon principle says that we shift to the right.
Yeah, if the H plus is gone, and then this one want to add back H plus, and then while adding back H plus, he also adds.
You're right. You will have extra of this.
Yeah, so this is why the CH3COO minus have a plus 0.001.
Yes. Good. You're right.
So it is traceable.
Yep, good. That's the way.
Yeah, that's good.
Yep.
And then what happens when you add an acid? When you add an acid, right, and then it'll be a second equation that it's like
No. When you add acid, the ion will want to form molecular state with the acid.
So you still
Back
don't
to
know.
this one.
So you
Now remember, once this is one way. So after we add, right, you no more this equation. You left this only. You only have the top equation after the solution is set up. Because this is one side. After dissolve, no more. So this equation will not exist anymore.
then what is this for?
This is to tell you how you can create a buffer solution. So,
So
this
it's
end.
just there for the buffer to exist.
You're
but
right.
when-
This one
when
forever
reaction
exists there.
happens, you will just look at the top.
You're right. This is one shot gone already. That's all become right hand side already. And the sodium is no longer in the picture. Okay.
So when you add acid,
Yeah, okay, let's do the explanation things. Okay, complete the whole story. Okay. It's good for my video anyway. Now you have in the explanation is very simple. All you need to tell them is a word. But this wording, okay, it will help you to see what to do when you add some value in the calculations and kind of things. So we have exit buffer, you have basic buffer, okay, and we have a retardate with H plus and retardate against OH minus, H plus and OH minus. Okay, so example of an exit. Okay, so CH3 COO H, and we give you CH3 COO minus with H plus. You will need a salt of it. Okay,
just to be present.
just to be present, and this is a one-time issue in this code. Okay, so the majority of this is contributed by this. Okay, so the idea is the first thing is how do we retaliate against H plus. Okay,
Actually, it does something. It does something like making the.
it's just introducing reinforcement ion only.
Oh yeah.
Yeah. Okay, and you just try to shift a bit backward in the beginning. Okay, so against H plus, right, we say the H plus, okay, will meet the CH3 COO minus, and then majority of them will love to stay within the
COH.
molecular form. So that's why the H plus added will be
So it will
retaliated.
cause the ion to drop and the acid.
Yeah.
will
So like you add H plus, most of them will be removed. So as if you didn't add
Yeah,
much
okay.
things. So against OH minus, okay, against OH minus, you say that OH minus is being removed by the H plus to form H2O.
Then by LCP.
Yeah, by De Châtelet's principle, okay, then it says that the CH3COOH, right, will shift the equilibrium to the right side, so we penetrate H plus and CH3COO minus. So this is why the H plus is more or less unchanged. Okay?
Can you go to the basic buffer?
Yep, basic buffer. So for the basic buffer,
For weak.
okay, example is just like
Base salt,
NH3, give me
NH4.
H2O, give me NH4 plus OH minus. Okay, so therefore you still have NH4Cl become NH4 plus and Cl minus. Okay, again reinforcement of ion
Yeah.
only. Okay, so the first one is that when you add a H plus inside, okay, how does it retaliate? Okay, H plus will react with OH minus. H2O by LCP.
NH3 will
Yeah,
replenish
you
the
are right.
OH minus.
Will dissociate back to NH4 plus to replenish the OH
So
minus.
this will cause the NH3 concentration to drop while the N H4 plus value to increase.
You're right, okay, but the idea is to remain the OH minus
Yeah,
is
but
more.
calculation we need to know.
Yeah,
that.
in calculation, once you say it this way, something drops, something increase, right? Okay. So
And
when you have OH minus added, okay, then the same thing, OH minus, right, will be
and the NH4
with the NH4 plus, right, will form back to the
very
molecular state.
readily form.
Yep.
Very readily form.
Yes, back to this.
And then so this will cause a drop in the
In
ion
this,
and an increase
And
in
then increase in this.
So that's one calculation.
Yes. Okay? So that's the explanation part.
Actually, I was confused on. I was thinking that the second equation, the sort one-time equation, has something to do with the.
Yeah, a lot of people think in this way.
Yeah.
It is workable, but not recommended. Really not recommended because conceptual wise it's very weak. See,
Yeah, so the only thing.
people
that,
what do they say? They say they don't use LCP. They try to avoid it. They will say, when it's in an acidic buffer, it says that when you add OH minus, right? They will say that, oh, you have something like CH3, COOH, and then we have a CH3, COO minus, and H2O. This will react with OH minus with this. Chemically is wrong. Will it react with this? I don't think so. Okay, but it's equivalent. Okay. They can do this. So they say, oh, once you add this, this one drop by how much, this one come out by how much, is the same thing. But the more correct one and makes sense one is actually the LCP things. In the explanation, you must use the LCP one. Okay. Okay, any problem? Any more problem? Okay, for the weak acid weak base one, just for your knowledge, okay, it won't be tested on calculations. Okay, the idea is that both salt form will undergo their own hydrolysis.
And you see which hydrolysis is strong.
Yeah, but how to really calculate which one because they are all interacting with one another. H plus OH minus.
So they know.
You just need to know why it can't be, how do we normally handle it? We just use pH meter. Can't even use any indicator. And at the end point, we have to define this and that. You will see that there are two buffer region and this and that. But just for self knowledge, okay? I don't see any kind of series that is really asking anything deep inside. Right, this chapter, okay? Great. I know it's a bit confusing, okay? But think in this way, okay? If after 1 or 2 weeks you spend on this topic, you still found that it's confusing or difficult, right? Something is wrong. You got to soon realize this is a very simple thing. Learn it in a very simple way. Okay? And how many formulas do you have? You have 1. Okay? So try to make your thinking and this kind of thing easier. Anything else you want to ask? Tired? Kinematic one? Anything? Next round. Next time.